Welcome to lecture 5.4, periodic forcing terms. So the goal here is, let's suppose we have a function that's periodic, and I mean of course a sine wave or cosine wave is periodic, but I'm talking more about a piecewise periodic function. We want to be able to compute the Laplace transform of this rather easily. So it's examples of these waves that, so for example, let's take a square wave, something like this. This is a square wave, and we might have a sawtooth wave, something like this. Actually, technically it should be this. You can draw these horizontal lines vertical lines if you want to. So this is a sawtooth. Or maybe we have a triangle wave, something like that. Triangle wave. So from what we learned in the previous lecture, we can compute the Laplace transform of a piecewise function by splitting it into a sum of Heaviside functions. But if you have something like this, then that's going to result into an infinite sum because we have an infinite number of little pieces. Fortunately, there is a better way to do this in terms of just what the function is on a periodic, I'm going to call it a window. Okay, so let's write that down. So here's the approach. Approach is to consider, so I'm going to say consider let me call it the window, and let me give it a new name, and call it f sub t of capital T, and it's going to be defined, t is going to be the period, so this is defined on 0 to t, and extended to be periodic. So in other words, we want to write this function f of t as this little window and then extended. I think it's better if I draw a picture. So let me first write this. So then f of t is, so it's just the window, or it's just this basic little function. Think of this as like our signal on 0 to t, and then it's going to be ft of t minus kt in this range. Oops, kt. So this thing here is the kth translate of the window. So I think it's better if I draw a picture now. So let's suppose that the window is something, let's suppose that I'm going to draw a function that is definitely asymmetric. So, well, I'm not sure if that's a proper function. Let's redo that a little bit. Let's draw this like that. And I'm going to call this f, so this is t, f big T of little t. And so now the function, the actual periodic function, is going to look something like this. It's going to be that, this thing repeated, okay, so now this thing here, this is t, 2t, 3t, 4t, and so forth, 5t. So of course this is the t-axis. And this little piece right here, let's actually do this in red. This little piece is f, this is the window, f is a big T of little t. Now this thing here is this thing shifted by t. So I'm going to write this as, this is f sub t of t minus big T. This thing here is this thing shifted by 2t. So this is f sub t of t minus 2t. This thing here is shifted by 3t. I'm going to keep doing this. So f sub t of t minus 3t. Oh, that should be big T. T, and this thing is f sub t of t minus 4t. See what I'm doing? Each one of these shifted translates of this is so I'm writing it as f sub big T of t minus kt. So this thing looks complicated, but all this is describing is that in the kth window, in the fourth window, this is the formula for what that function is. Okay, so let's make a remark now. This is about something I talked about last lecture. This function, f sub t of t minus, well, let's actually back up a bit. This function we can, of course, multiply by the Heaviside function. Right? That doesn't do anything to it. It just multiplies it by 1. So each of these we can multiply by the Heaviside function, and it doesn't change it at all, but we can multiply each of these by the shifted Heaviside function. So in other words, how about this? Let's go up here, and I'm going to write this. This is the same thing as f. This is exactly the same thing as this function. I can stick a Heaviside function in front of it. So therefore, each of these is a shifted value of this thing up here. So in other words, this function is just a shifted value. It's f sub t of t minus k big T times h of t minus kt. You may be asking, why are we doing this? Well, here's why. Because now I can write, how do I want to write this? Let's do this. My function, f of t, my original function, I can just write that as an infinite sum of this plus this of each of these pieces. So in other words, I can write this as the sum from k equals 0 to infinity of f sub t of t minus kt times h of t minus kt. And that's going to be helpful in computing the Laplace transform. Okay, so next, let me write down a key point. This is something. So here's a key fact, and you likely remember this. This should ring a bell from basic calculus. When you studied infinite series, is if you have a number, let's call it x, which is less than 1 in magnitude, so it's some fraction like 1/2 or 1/3, then the infinite sum, 1 plus x squared plus x cubed, etc. If you prefer, you can write this as the sum from n equals 0 to infinity of x to the n. That is just equal to 1 over 1 minus x. So let me box that. That's important. Okay, so why is that important? Well, let's apply that to evaluating this infinite function. Well, not to evaluate the infinite function, but I should say evaluating the Laplace transform. So this is what we want. So what we want to do next is, what we want to do originally is compute the Laplace transform of this function. So we're going to do that by computing the Laplace transform of the function written like this. Okay, so let's do that. So let's write f of s. So the Laplace transform of this bugger is just the it's the sum of the Laplace transforms of each piece. So it's the n equals. Actually, I think I called it k. Yeah, let's speak in k equals 0 to infinity of the Laplace transform of this thing, ft of t minus kt times h of t minus kt. Okay, so that's the Laplace transform. And now remember, we have a formula for how to compute this. Right? It's just the Laplace transform of this thing shifted by e to the minus cs. And let me write up why that is. Recall that the Laplace transform of f of t minus c times h of t minus c equals e to the minus cs times f of s. I told you this would be useful, so we're just applying this formula down here. So this is the infinite sum, k equals 0 to infinity, of, so e to the minus cs. So c here is k times t. So that's going to be our c. It's going to be our c. And you can see that because it's here as well. So e to the minus c s is e to the, does that look like an e? I can do it a little better than that. E to the minus c times s, so is minus k times t times s times whatever the heck the Laplace transform of this function right here is. So let's call that, as we've been doing, capital F sub t of s. Okay, so this is the Laplace transform. This is it. However, we can actually do better than this. We can simplify it. Notice that this thing we could just pull out of the sum. This is a function. There's no k in here, so we can pull that out in front. And I can write this as f sub t of s times the sum k equals 0 to infinity of e to the minus k ts. Okay, so this is it. This is the Laplace transform of the periodic function. So to summarize, if we have a periodic function like this, the Laplace transform of this is the Laplace transform of the window times this infinite sum. And actually, this infinite sum we can simplify using our knowledge from basic calculus. And if you don't remember the details of that, that's fine. I don't need you to be able to answer series and sequence questions in this class. We just have to be able to use some of the big ideas. Okay, so let's write this down here so that this is equal to. So what are we going to do? We're going to apply this rule right here to this thing right here, that infinite sum. Okay? So I'm going to rewrite this as, let's get my pen back, f, that's the Laplace transform of the window, times, now this sum, I'm just going to subtly rewrite this using basic laws of exponents. K equals 0 to infinity. So I'm going to pull the k out in front. So I'm going to say e to the minus s times t. And then I'm going to put a k out there. I can do that. You can't stop me from doing that, right? And now this is going to take the place of my x. So I can write this as an infinite sum, n equals 0 to infinity. Actually, let me not quite. Let me delete that and let's see if I want to. How about this? I'm going to move this up here. Okay, and now I'm going to say this is, I'm going to rewrite this thing up here. And so this is f sub t of s. And now, again, this is just my x. So this whole infinite sum is 1 over 1 minus this thing. So times 1 over 1 minus e to the minus s. Let's fix that up a little bit. S times t. So this is, let's double box that. This is the Laplace transform. Put a star by it. This thing is the Laplace transform of a periodic function like this. So to summarize, all we did is we computed the Laplace transform of a single piece, this window, multiplied it by this thing, And that's the Laplace transform of the entire periodic function. Let's do an example. Let's compute the Laplace transform of a square wave whose fundamental window is this here. Let's sketch what this would look like. So we have here's the t-axis. So let me mark off integer points. So that this is 1, this is 2, this is 3, etc. So the square wave is going to have, let me do it in red first. So here's the fundamental window. And then when we repeat it, it's going to look like this. So if you want to, you can draw these vertical lines. It's this square wave. Okay, and it just repeats like that. Okay, so recall from last time that the the Laplace transform is, all we have to do is compute the Laplace transform of the fundamental window, and then we have to multiply by 1 over 1 minus e to the minus s times t. In this case, t is the period, so I should say that t equals 2. Remember the capital T is the period, so e to the minus 2s. So all we have to do now is compute the Laplace transform of that window right there. Okay, so let's do that. First we have to, I guess the first thing we have to do is express the window using the Heaviside function. We actually don't have to do that. We could compute the actual integral, but let's do it this way. So this is, get my pen back. This is h, it's the interval function times 1 minus the interval function at 1, 2. So it's this interval function minus this interval function. Okay, so let's do this using shifted Heaviside functions. This is h of t minus h of t minus 1. And then let's subtract off h of t minus 1 minus h of t minus 2. And let's simplify this, and now we get, this is h of t. We have negative 2 h of t minus 1s, because we have negative 1 here and negative 1 there. And then we have plus 2h of t minus 2. Not plus 2, sorry, we just have plus 1. So plus h of t minus 2. Okay, so the Laplace transform of this window, capital F of s, is, so it's the Laplace transform of the Heaviside function, h of t, minus 2 times the Laplace transform of h of t minus 1 plus the Laplace transform of h of t minus 2. So we know how to do these. This first one, this is just the Laplace transform of 1, which is 1 over s. The next one is, this is also, remember this is 1 over s, but it's shifted by 1, so we have to write this as 1 over s times e to the minus s. And similarly this is the function 1 shifted by 2, so we have to write 1 over s times e to the minus 2s. So if we want to, we can write this together as, or we can combine terms and write this as 1 minus e to the minus s. Oh, let's fix that up a little bit. E to the minus s. Is that curve? Hold on, let's try this again. I think I'm trying to think too many steps ahead. So this is 1 minus 2 e to the minus s plus e to the minus 2s over s. And yes, this is what we can do this. This is actually a square on the top. You don't really need it, but I think it'll be helpful to write this as 1 minus e to the minus s squared over s on the bottom. So this is the Laplace transform of the window. So now we just have to, well, now we're almost done. All we have to do is multiply by this thing, and then let's simplify. So let's do that. The Laplace transform of the square wave is, again, it is the Laplace transform of the window times 1 over 1 minus e to the minus 2s. So that is, I'm going to write this out because I think something is going to cancel. E to the minus s times 1 minus e to the minus s over s. And now I'm going to stick this thing right down here. This thing is a difference of squares, so I can write this as 1 minus e to the minus s times 1 plus e to the minus s. Do you agree that this thing here, that thing here is just the same thing as that thing there? Okay, so now that's going to cancel with that, and we can simplify this as 1 minus e to the minus s over s times 1 plus e to the minus s. And that is our Laplace transform of this square wave. So we will finish this lecture by solving an initial value problem where the forcing term is that square wave from the previous example. So let's sketch what that square wave looked like. It was just a simple square wave that like this. This is 1 and this is 2. Okay, so the first thing to do, as before, or as we've always done with these things, is apply the Laplace transform to both sides. So first step is always apply Laplace transform. So we get the Laplace transform of y double prime plus the Laplace transform of y equals the Laplace transform of the square wave. So if we simplify this, let's see, we get it's going to be s squared y minus s times y of 0 minus y prime of 0 plus y equals 1 minus e to the minus s. This is what we did on the last slide, times s times 1 plus e to the minus s. Now these things are both 0 because our initial values are both 0. So this makes it a little bit simpler. So when we go down here, let's write this as, so we have s squared plus 1 times y. And notice I always like to write the thing in parentheses before the y, otherwise it looks like y of s squared plus 1, and that's not right. So that's going to be 1 minus e to the minus s over s times 1 plus e to the minus s. Okay, so now we can solve for y, which is, remember, it's one of our big milestones whenever we can solve for capital Y. Now I will write y of s. This thing is 1 minus e to the minus s over s times s squared plus 1 times 1 plus e to the minus s. So this is big Y. So whatever our solution to this initial value problem is, this is its Laplace transform. So now all we need to do is somehow simplify this, and this, it is a little complicated. So let's recall something from partial fractions. I think I did this, I think the previous lecture. Call that 1 over s times s squared plus 1. Well, actually, I think this one was a little bit different, but this thing here, it's easy to check, is equal to 1 over s minus s over s squared plus 1. So that's something that we will use. So we can write this as, so let's pull out that part, 1 over s times s squared plus 1, and then the other part is 1 minus e to the minus s over 1 plus e to the minus s. So this thing here, we know what to do with this. So this thing here, we just apply that rule. And then this thing here, we need to simplify more. So we need to simplify. Okay, so how do we simplify this? And there's a little bit of algebra tricks in here. Nothing too bad. So, okay, let's write it out down here. So 1 minus e to the minus s over 1 plus e to the minus s. So I'm going to write that as follows. I'm going to write that as minus 1 plus e to the minus s over 1 plus e to the minus s. And then I'm going to add 2 over 1 plus e to the minus s. It may seem, you may be asking, why, where did I get this from? It's actually a natural thing to do because once I write this term, these things are going to cancel, and that makes things easy. And this thing is definitely easier than this thing was. So it's not that unnatural of a thing to do. So let's see what else I want to say about that. So this thing here, again, well, that's just going to cancel. So this gives us negative 1. And this thing here, what do we do with this? Well, remember our little trick that the sum of n equals 0 to infinity of x to the n equals 1 over 1 minus x. Remember that? Well, this thing looks similar to that. I should also mention that if we have n to infinity, if we have negative 1, or let's write it like this, negative x to the n, that's just the infinite sum of negative, actually, let me just write that as, so this is 1 over 1 plus x, because it's 1 over 1 minus negative x. Okay, and that's, and anytime you see a negative x to the n, you can always write this as negative 1 to the n x to the n. I think you may have seen this form more when we studied alternating series in calculus. Anyways, this thing we can use, we can write as an infinite sum. So let's do that. Let's write this as, so this is negative 1, let's not forget about this term, plus this is 2 times the sum from n equals 0 to infinity of, oh, actually, yeah, let me, before I do that, let me write this as 2. Wrote wasn't wrong, I just want to add an intermediate step over 1 over 1 minus negative e to the minus s. So now you can see that this is the x that's going to come into play with this formula up here. So now I can write this as negative 1 plus 2 n equals 0 to infinity of negative 1 to the n times e to the minus s times n. Actually, again, I'm having second thoughts. I should insert an intermediate step. So I should say negative e to the negative s to the n. Okay? And now let's go back over here. That's negative 1 plus, this is what I was going to write, n equals 0 to infinity of negative 1 to the n times e to the minus n times s. Okay, so that's helpful. So now we can go back to, where were we again? Remember this thing is what we had, and this we broke up with partial fractions, and this we successfully simplified, and this is what we simplified it to. So let me let me box this. So now we can write y of s equals, this term is going to, let me write this down here, so that's going to be 1 over s minus s over s squared. I'll write that, do better than that, s squared plus 1. And then this thing here I can write as, just put that there, as negative 1 plus the infinite, hold on, I guess I forgot my 2. I had a 2 there and I dropped it there, so let me stick that in there. So plus 2 times the n equals 0 to infinity, and then negative 1 to the n, and then e to the minus ns. Okay, so what do I want to do now? Let me give this a name. This thing here, I'm going to call g sub g of s. And if I do that, then this thing simplifies to g of s times negative 1 plus this thing. And actually, let me do one more thing. So in this series, the n equals 0 term is 1 times 1 is 1 times 2, right? So I'm going to take this series and I'm going to start it at 1. So again, the n equals 0 term is 1, and there's a 2 out here, and that is going to cancel with this negative 1. So I'm going to start from 1, and I'm going to make this negative 1 term positive 1. Okay? And that's going to make things a little bit easier, because now we have y of s is, so again, I'm going to multiply this g of s times 1, and then the g of s times this. So that's going to make this g of s plus 2 times this sum, n equals 1 to infinity, e to the minus ns times g of s. So I'm going to put that g right here. Okay, so g is, now here's where I want to show you that formula from the Laplace transforms that keeps coming up time and time again. See where I can fit it. I can do it here. So recall that the Laplace transform of f of t minus c times h of t minus c, that thing is just e to the minus c times s times the Laplace transform of s. So we're going to apply this formula. I told you it was useful. This formula we're going to apply to this thing right here, to this g. So g of s is, so what is g of s again? G of s is, where was it? It was this thing. So note that, so what's the inverse Laplace transform of this thing? The inverse Laplace transform of this thing goes to 1, and this thing goes to cosine of t. So g of t equals 1 minus cosine of t. Let me box that. So that's what we need to apply this formula in reverse. So if this is the Laplace transform of this solution, so the solution is y of t equals, so it's the inverse Laplace transform of this. We just did that as 1 minus cosine of t. And then it's 2 times the inverse Laplace transform of this thing. So let's see how I want to, just trying to think how I want to organize things. So notice that, so let's put another, add to this note down here below, that the Laplace transform of g times t minus n h of t minus n, that is just e to the minus n times s times g of s. And that is what we have right here. So let me also box that. So basically we're just applying this formula in reverse, our super useful formula, to this each term of this sum here. So that's going to make this 2 times the sum from n equals 1 to infinity. The negative 1 to the n, that just sticks around, that's just a constant. And now this thing here, again this, the inverse Laplace transform of that is just this guy here. So that is g of t minus n times h of t minus n. Okay, so this is, let me box it. This is our final solution. I'm going to simplify this a little bit more. But to summarize, we have a differential equation, initial value problem, where the forcing term is a square wave. It makes sense, right? You know, you have a harmonic motion, maybe an electrical system, and the forcing term is this square wave. Though the solution to that initial value problem is precisely this thing right here. So I'm going to clear everything on this slide, and I'm going to say a few more things about this before we finish. Okay, so let's summarize what we did in the previous slide. We had an initial value problem, something like this, with these initial conditions, and the forcing term is this square wave. So we first took the Laplace transform of both sides of this equation. That's what we always do. And we did that. We solved for capital Y, and we get this expression here. So we call this thing big G of s down here. And then if we call this big G of s, then we multiply through, and it's G times 1 plus G times this thing. So we move the G inside here. And now big G it's easy to compute the inverse Laplace transform. That's right from the table. This goes to 1, and this goes to cosine of t. And then the inverse Laplace transform of this side, this is set up perfectly for our formula from the previous lecture. So using this formula, we see that so the inverse Laplace transform of this is just g of t, but it's shifted by n. So plugging it right in, we get this, and this is our solution. So let me actually go from here and plug 1 minus cosine of t back in here. So this is 1 minus cosine of t. And just for the heck of it, let me multiply by h of t, because I have 8 heaviside functions in this term. And plus 2 times this sum. And now let me, instead of putting g of t minus n, let me put this back in here. So that's going to be 1 minus cosine of t minus n times the heaviside function h of t minus n. So this is probably the best way to write the final solution. I don't think you're going to write it in form better than this. Let me just say a few words about this. So this is a superposition of infinitely many waves. Oops, I didn't mean to do that. However, notice, even though this is an infinite sum, if you so you're adding up infinitely many things like this, but each of them gets shifted to the right more and more. So, for example, cosine, so this term, 1 minus cosine of t minus 10, this times the heaviside function, this thing doesn't start until t equals 10. So if you actually plot what this looks like, got this from a book example, so it's not at all, there's no way it's clear looking at what it's going to look like other than it's some sort of superposition of cosine waves. So this is 0.7. So this is the y value, this is the t value, and say that this is 10 and this is 5. And this function turns out that it goes up to about 0.7, then it does something like this, and then and I'm just doing a very rough sketch. So something like this. It's not periodic. Nothing here is ever going to repeat, it turns out. And again, if we chop it off at 10 and look at what function is this thing, this window, then it's only going to consist of the first 10 terms from here, because the n equals 20 term is 1 minus cosine of t minus 20 times h of t minus 20. So that thing doesn't even, that gets chopped off left of 20. So even though this is an infinite sum, for any finite window, it's a sum of only finitely many cosine waves.